So I just want to go back to this idea we started at the beginning of the semester, the course in some. So just so this idea that so in probability on the one side, like we discussed, is the study of models. For random experiment. And the crucial thing is, this is applicable when the model is known. Statistics, on the other hand, is built on, is sort of decides how to study the experiment when the model is fully not known. So here one tries to, when the model is fully not known, one tries to infer about the unknown object. Aspects based on the outcome of an observed experiment. Of course, the theory of probability stands in strong ground because there's a connection between the two in some specific way, which we'll illustrate today. So the first thing we do is so one observation you can do is that so the setup we will assume is that in the following manner. You perform an experiment n times. And let's say let us be interested in an event A. So A is an event of our interest. Let me just copy this and put it at the top. That's most space on the page. Very nice. So now we perform an experiment n times, and let us be interested in the event A. So the probability model will give you P away. In statistics, you can only observe the outcome, right? So let's say there's a hidden model, unknown model in the background that governs the experiment. And provides probability of it in some case, whatever that means. Okay? So some number it provides for it. So if you knew the model, then you would understand what P of A is. Unfortunately, the model is not known. Right? So now, if the model is not known, then one needs to sort of understand how does this P of A relate to what we see from the experiment. So we have performed the experiment in time. Now what you do is you just the event A. So you define xi to be 1 if the event A occurred in the ith trial and 0 otherwise. So then the first thing we would do is we would make some assumptions that each trial of the experiment is identical and independent of each other. So we would make that assumption. Very good. Once we make the assumption, then what we do is to understand the event A, we would so in statistics we would just go and say, okay, let's compute the relative frequency of A, of occurrence of A. So what is the relative frequency? That is the same as the number of times A occurs in n trials divided by the total number of trials, which is n. But this in our notation is just the same as, if you look at it, A will occur if xi is 1 and A will not occur if xi is 0. So you can just look at it as the sum I equal to 1 to n of xi divided by n. So the relative frequency of the occurrence of A is given by number of times of A occurs in n trials divided by n, which is summation xi by n. So here we'll make one small extra observation. If you assume this, that each trial is independent, it's just saying that each xi is identically distributed and independent. Right? That's what this is. That's the setup we have. So now somehow, so on the one hand, I'll recap a little bit. On the one hand, if the model is not known, we don't know what P of A is, but we're interested in the event A. A is our key interest. We want to know what P of A is. So what we do is we go out and perform the experiment n times, with each trial being independent of the other. Once you do that, you can compute the relative frequency of the event A. And from this, one tries to infer what can we say about P of A. And in statistics, all we have is summation xi by n. Now, is this kind of close to P of A or not close to P of A? Very nice. 3. So how does one begin the analysis? So this is the crucial connection one has to do between relative frequency and probability. Let me call this as star. This is one place we have. And we'd like to understand its connection to, let's say, let's call this as double star. So star and double star, are they close by or not? In what sense are they close by or not? Very nice. So here are some observations. So what's the first observation you can make? The first observation is the following, that so let's say let's make a simple observation. Let's say a simple notation fix. Let's say P is the number problem here. We don't know what P is, but let's say P was the number problem, the true problem here. So this is the true problem here. So this is in the assumption that the model is known. But what we know, what we observe is 1 over n summation I equal to 1 to n xi. And this from the experiment. And what did we say xi was? Xi was equal to 1 if A occurs and 0 otherwise. That's what it is. 1 less than equal to 5, less than equal to 1. Or I should not say this, I should just say we observe this, we observe this, we observe this. Observe this. And then we said that, okay, fine, we're going to understand the relative frequency of A to be equal to 1 over n summation I equal to 1 to n xi. Well, so now the thing was, how close is the relative frequency? And this we also know from before, this is just the sample mean x bar. So now let's do some computations. This is the first observation. Observation 1 is this. Okay, 1. This is what we do. Let's set up. The second setup we already have done, but let me just do it again in this fashion. The observation is that xi are all identically distributed. And independent. That is, xi's are IIDs. So now, so let's look at x1. What's E of x1? E of x1 is just going to be equal to, E of x1 is 1 if probability if A occurs, and 0 if probability if A doesn't occur. So that means E of x1 is just 1 times the probability of A plus 0. So it's the same as probability of A, which is just my number P. So that's the number. And since all xi is the same distribution, this would imply, given xi is IID, so we'll write it down in green or blue, let's say, given xi is IID, that is, they all have the same distribution, this will imply that that E of xi is equal to. Now, the simple calculation, one can immediately show that for all. A simple calculation, one can also show the following, that E of x1 squared is also the same as simple exercise to not the half. Because you just put 1 squared, xi takes 1 and xi 0, so xi squared is the same as xi, so E of xi squared also is x1 squared. So this would quickly tell you that the variance of x1 is going to be equal to E of x1 squared minus E of x1 the whole squared, which is just going to be p minus p squared, which is just p times 1 minus. So let me just use our notation. Let's leave it as it. So let me call this as let's just notate, this is use notation p times 1 minus p as sigma squared, and the mean mu is called p. Very nice. So that's second observation. And again, like before, given that xi is or IID, this will imply that variance of xi is equal to p times 1 minus p, which is the same as sigma squared. Very good. The third observation is the following, that you look at what we have in our object is x bar, right? That's x bar, which is just summation I equal to 1 to n of xi divided by. So now we do the same thing again. We just look at E of x bar. So this would imply that E of x bar, the mean of on average is going to be equal to the sum from I equal to 1 to n E of xi divided by, and that's just going to be equal to, just everybody's going to be p times n divided by n, which is what we just showed about, right? Each of the xi's had mean p, so it's going to be n. And now, again, you know that the variance of x bar is the variance of summation I equal to 1 to n xi by n, which is the same as 1 over n squared times the variance of summation I equal to 1 to n xi, the rules of our variance. And now, since they are independent, so here I'm using independence. And this will be equal to the sum of I equal to 1 to n variance of xi, the whole divided by n squared, and that I will just denote it as n times p times 1 minus p by n squared, which I will call it as p times 1 minus p by n. So this is just notation wise, let's just call it as sigma squared by n, and let's just call this as notation wise. So it means we have shown that E of x bar is mu and variance of x bar is sigma squared by n. Now let me come back and finish the calculation. Now what is this telling you? This part is telling you on an average, let me move this down. Colorfully going down. So here, one observation here is that, on an average, x bar is equal to its true value. Okay, equal to its true value. That's what this line means. Right? That means, in terms of understanding relative frequency and probability, what you do is that if you repeat an experiment many times, n times, you get some number. You repeat this process again, then you should get value. That's one way of interpreting this line. We'll make that precise in a second. What does this mean? What does variance sigma squared mean? This means that is the spread of x bar, right, or the range of x bar is getting smaller and smaller as n gets larger and larger. Smaller as n gets larger. And this is what we said long time back. That SD signifies that the range of x bar was going to be what now? The range of x bar, we know, is kind of close to its true value, that is its mean, right, plus standard deviation, right, plus or minus. So on this side I'll have minus sigma squared by n plus mu, or on this side I'll have mu plus sigma squared by n. So this interval is getting smaller and smaller as n gets larger and larger. So I should not say, I'm sorry, I made a mistake. It's standard deviation. So it is mu minus sigma by root n and mu plus sigma by root n. That would be right. So now I know my x bar is getting, in this calculation, I know my x bar is getting closer and closer, is equal to mu on average, and the variance is getting smaller and smaller. So can I make this understand this a little better? So that's the final conclusion we can draw in this idea. So let epsilon positively given, right? And what are the interests? Our interest was we had probability of A as a number. Let's call that as P, right? P was probability of A. Minus what we calculated from the sample was summation from the experiment or the sample was summation xi by n. Right? How far is this? Can I understand this event? That can we understand this event? Can we quantify this event? What is the probability of what is the probability of this event? That is the chance that x bar is from P at least epsilon. Right? This is what we want. That will give you an idea of how star is close to double star. So for this, we rewrite it a little bit. So we just write it in normal notation, same as when we put a question mark. What is this? So to understand this, I will do the following. So I will just rewrite notation a little bit. So now we know P is, xi is I isn't equal to 1 or all identity distributed. So and then I'll call mu, which is E of x1, was indeed equal to P, and sigma squared, which is the variance of x1 or xi for every I, was equal to P times 1 minus. This is what we have. These are both finite numbers for all I and independent. Now, look at this expression right here. So the above is the same as if I understand the chance that I have x bar minus P is just mu, or right, mu is bigger than epsilon, is what? Is equal to 1. So the above is same as this, right? But what is this equal to? But now I'll do a little trick. I'll do probability of x bar minus mu is bigger than epsilon. I'll multiply and divide by epsilon, the sigma. I'll divide by sigma and multiply by sigma. Above is equal to this. Now this we know by Chebyshev. Because x bar, we also know that. So I should is equal to this. That's easier. We also know that from the above calculation, E of x bar is also the same as mu, and we know the variance of x bar is sigma squared by. Right? So here I would divide by sigma by root n, sigma by root n, and I multiply by sigma. So now I have a random variable x bar, its mean is mu, and variance is sigma squared. So let me try to use different colors so it's clear. So same as x bar minus mu is bigger than. So this I'll do the algebra. I'll write it as root n epsilon by sigma and times sigma by root n. So now I can apply Chebyshev's inequality. Right? Equality, right? Equality. And what do I get now? I think this here. And what do I get now? This less than equal. I have this 1 over k squared, right? So 1 over k squared is just 1 divided by root n epsilon by sigma whole square. And that's the same as the rewrite this whole thing. It's sigma squared by n times epsilon. Very nice. So what have I shown? I've shown the probability of the event x bar minus mu bigger than epsilon is of the order sigma squared by n epsilon. So what have I shown finally? The punchline is that the limit as n tends to infinity, the probability that x bar minus mu bigger than epsilon, or let's even better. Let's do this. Let's rewrite in our own language. Limit of of P minus 1 over n summation I equal to 1 to n. One over n, that's what we observed in the experiment. This person bigger than epsilon is going to be 0. Right? That's what we observed. So we put all this in blue there. It's clear. Let's say the limit as n tends to infinity, the probability of this is equal to 2. For any epsilon. And this is much more generally known. This is called the weak law of large numbers. So this tells you that the relative frequency and the true probability are kind of close together in this manner. So this, let me write the theorem down. So the theorem is the following. That theorem is that this is called the weak law of large numbers. It's called the weak law of large numbers. This says that let x1, x2, xn be a sequence of independent and identically distributed random variables. You assume x1 has finite mean, that is, x1 has finite mean mu and finite variance sigma squared. Right. Then, for any epsilon positive, the limit as n tends to infinity, the chance that x bar minus mu is bigger than epsilon is equal to 3. So where x bar is 1 over n summation I equal to 1 to n. This is what we have proved. It's called the weak law of large numbers. So in some sense, from our specific example above, so we have shown that the relative frequency connects to probability. And the way we did that was we took xi in a specific form. Let me just recap this discussion and then I'll say something very strong, much stronger, and try and put that strong statement out there. So what did we do? We said that we were interested in understanding what P of A was. We don't know what P of A is because the model is not known to us. We perform an experiment. X1 gives some outcomes. We call the outcomes 1 if A occurs, if 0 if A doesn't occur. Each star is independent, so the Xi's are all IID, that is identically distributed and independent. And you can compute the relative frequency of A by looking at the number of times A occurs in n trials divided by it. Well, that's the same as summation Xi by it. And what are your observations? Observations are P is the probability of A. You observed Xi's. You also know that E of x1 is P, that means E of xi is P. Then E of xi squared is also P. So the variance of xi is just P times 1 minus P, which I just call it as sigma squared. Then from that, I observe that the relative frequency, which is summation xi by n, which is x bar, also on average is equal to p. And the variance of x bar is sigma squared by n. So getting smaller and smaller. That means the range of x bar is getting smaller and smaller. So in some sense, the relative frequency is getting closer and closer to the value p. Or in this case, I just notation of mu. So ultimately, what are we interested in? We're trying to understand the chance of the event, the relative frequency, is away from the probability that we're interested in. Yeah. But that's the same as adding in a little fancy way that how far is x bar, that is sample mean, from the true mean. Product one. That's the same as I just do an algebra. I just get sigma epsilon by sigma by root 10 and sigma by root 10. I multiply it out. I get this. And that's the same as 1 over root 10 epsilon by sigma. That's sigma squared by. Now you know that this part goes to 0. In a sense, what we've shown is for any fixed epsilon, the limit as n goes to infinity, the probability of this event is equal to 0. So that's sort of a very strong, powerful statement. And in this mechanism, we have shown that the relative frequency approaches the true probability as n goes to infinity in this particular case. That gives us a statement of weak law of large numbers, which we have shown in this argument. That is, if x1, x2, xn be a sequence of independent and independent variables with finite mean and finite variance, then for any epsilon positive, probability of x bar minus mu within epsilon is equal for x bar. Very nice. Very good. Now I'll conclude this section by saying the following, that this above statement is true in a much more general manner, much more specific manner. So we can come back here, make it bigger. So what's actually true is a stronger statement in this. It's not quite just that the probability of a sequence converges as n gets larger and larger. What's true is a much stronger statement, which I will write down. The theorem is the following. This is called the strong law of large numbers. And the result is the following, that again, the assumptions are the same. So let me copy it down. Let's say f, x1, x2, xn, finite mean. Let's assume finite variance for time being, because I don't need that. So doing this, let me write down here. So, let the stronger statement, which will require some more hard work to show, let x1, x2, xn be IID sequence of random variables. Let's say E of mod x1 is equal to mu, is finite. It's finite. E of x1 is equal to mu, and E of mod x1 is finite. And mu equal to E of x1 is finite. So now we have this. Then the following is true. Then, and let's say let x bar be equal to 1 over n summation I equal to 1 to n of xi. Then in the above we have shown the limit as n goes to infinity, the probability of how x bar differs from mu goes to 0. But here what we do is we show a little bit stronger statement. We show that the probability that the limit as n tends to infinity, look at the event when x bar, look at all the sample points for which x bar is equal to mu. X bar depends on n is equal to mu. This probability is actually equal to 1. So this is called the strong law. That is, actually with probability 1, your x bar approaches mu. it's not that your x bar differs from mu goes to 0 in probability for every fixed epsilon, like the above statement. This statement says that x bar converges to mu with probability 1. So we just write down the two observations. That is the weak law of large numbers, that is WLN, weak law of large numbers, weak law of large numbers. What does it say? It says that for every epsilon positive, the limit as n tends to infinity, the probability that x bar differs from mu up to an epsilon, this converges to 0. The strong law, on the other hand, that is SLLM, that is the strong law of large numbers, is a little stronger statement. In the sense, it tells you that no, I don't have to do this. I look at all the event where the limit of x bar is actually equal to mu. I just look at all these points for which the x bar approaches mu. And the probability of this event is actually equal to 1. So the exercise to check that this is a much stronger statement in the weak law. The proof of strong law is sort of non-trivial and hard to do. The weak law sort of follows from what we learned. Let me just quickly recap and I'll stop this discussion. So here's the fundamental idea that the weak law tells you that the relative frequency and probability are close by in this manner. That is, the event that the relative frequency differs from the true probability by epsilon goes to 0 as n goes to infinity. But the strong law tells you the relative frequency actually approaches the probability with probability. These are two fundamental pillar stones in probability and give this whole edifice that how relative frequency is controlled by probability.